This first video on astrophysics gives a brief summary of what we know to date about the various objects that make up the universe. As always on this channel, you can expect a clear and concise explanation of each topic. Please don't forget to click on the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. By any terrestrial standard, the scale of astronomical objects is enormous in mass, luminosity, distance, size, and age. The distances involved are so great that rather than using meters or kilometers to measure distances, astronomers generally prefer to deal with smaller numbers and have introduced the alternative units for distance. There are several units of distance used in astrophysics that you need to be aware of. A natural starting point as a unit for astronomical distances is the mean distance from the Earth to the Sun. This distance is called the astronomical unit. This distance was calculated from Kepler's third law. The astronomical unit is only appropriate on interplanetary scales, as the distances to other stars are so great as to render it too small to be useful. The light year is defined as the distance traveled by light through space in 1 year. To calculate the distance of a light year, you simply need to multiply the speed of light by the number of seconds in a year. For distances between stars, astronomers use a unit called parsec. The term parsec is a combination of parallax and arcsecond, which derives from the use of triangulation when measuring the distance between two stars. In order to understand how the parsec is defined, we need to look at some trigonometry and what is meant by parallax. As the Earth goes around the Sun, the nearby stars seem to change their positions very slightly with respect to the faraway stars. This apparent motion, it's not true motion, is called stellar parallax. A parallax is a periodic shift in the apparent positions of nearby stars due to the changing position of the Earth in its orbit around the Sun. In the picture below, you can see how parallax is used to measure the distance from Earth to near stars. Astronomers can measure the angle that the star appears to shift relative to very distant stars when viewed 6 months apart. First, the apparent position of the star in July is noted when a diagonal line is drawn between the Earth position and the apparent position of the star. Second, the apparent position of the star in January is noted when a diagonal line is drawn between the Earth position and the apparent position of the star. Next, a line is then drawn between the Earth position and these months and the center of the Sun. This straight line will become the base of a triangle. The tip of the triangle is the true position of the star to the base of the triangle. The line labeled capital D is the actual distance to the star. Since astronomers can determine the angles within the parallax triangle, they can calculate the line D. In this way, they can accurately measure the true distance from the Earth to the star. By using simple trigonometry, we can show that the parallax angle phi, measured in radians, is related to the distance d of the star by simple trigonometry. Since d is very much larger than one astronomical unit, parallax angles of all stars are extremely small. so we can always use the small angle approximation. The angle phi is very small and tangent of phi approximately equals phi. The sine of the angle phi is approximately equals phi as well. In figure below, the size of the parallax angle has been much exaggerated for the sake of clarity. Note the distance from the Earth to the star and the distance from the Sun to the star can be considered to be equal for such very small angles. The parallax of even the closest stars is very small because of the long distances involved, and this means that the parallax angles are so tiny that astronomers use arcseconds to measure very small angles. So, to determine the distance from Earth to a star, we must know how to convert arcseconds to radians. We know that 1 radian equals 57 degrees, 17 minutes, 45 seconds. We know that 3,600 seconds make up a degree just as 60 seconds make up a minute. And if we now measure all angular size in the unit of arcseconds, we will obtain a simple formula for converting arcseconds into radians. If we now substitute this into the equation above, we get let's see how it works. Barnard's star has a parallax angle of 0.55 arcsecond. What is its distance from the Earth in astronomical unity and in meters? We use the formula above to find out the distance we are asked for. We can see that the astronomical unity it is a very useful unit for measuring distances within the solar system, but it's too small a unit to express the distance to stars and galaxies. Therefore, for distances between stars, astronomers use a unit called parsec. We are now in a position to define the distance unit parsec. 1 parsec is the distance at which the observed parallax angle of the star is equal to 1 arcsecond, 1 second of arc. We can rewrite the formula. Writing our parallax formula in this way allows us to define a new natural unit for distance in astronomy, the parsec. Let's solve another example. To solve part A, we replace the parallax angle with 0.772. To solve part B, we multiply 1.3 parsec by the value of 1 parsec in astronomical unit. To solve part C, we multiply the distance in astronomical unit by the value of 1 astronomical unit in meters. Then we divide by the value of 1 light year in meters. The table below shows the relationship between the units of distance. Astronomers classify objects into various groups based on characteristics and locations in our universe. The first astronomical object you should know about is called galaxy. Galaxies are large groupings of stars, dust, and gas in space that are held together by gravity. Galaxies come in variety of size and shapes. There are hundreds of billions of galaxies in the universe. There are four types of galaxies: spiral galaxies, elliptical galaxies, regular galaxies, and lenticular galaxies. Spiral galaxies appear as flat, blue-white disks of stars, gas, and dust, with yellowish bulges in their centers. Spirals are actively forming stars and comprise a large fraction of all the galaxies in the local universe. The youngest stars form in gas-rich arms, while older stars can be found throughout the disk and within the bulge and halo. Elliptical galaxies are shaped like ellipses. Elliptical galaxies are made up of mostly of old stars and do not have much gas and dust. There is very little new star formation in these galaxies and show very little organization or structure. The stars orbit around the core in random directions. The largest galaxies we see are elliptical, but elliptical galaxies can also be small. Irregular galaxies do not have a well-defined shape and are not as symmetrical or regular like ellipticals or spirals. Some galaxies may have a rather weird structure. They are among the smallest galaxies and are full of gas and dust. Having a lot of gas and dust means that these galaxies have a lot of star formation going on within them. This can make them very bright. Lenticular galaxies are a kind of cross between spirals and ellipticals. They have the central bulge and disk common to a spiral galaxy, but no arms. But like elliptical galaxies, they have little dust and interstellar matter. Thereby, they have older stellar populations and little ongoing star formation. Despite all this, however, they are perhaps the most poorly understood galaxies. The second astronomical object you should know about is called a star cluster. A star cluster is a group of stars that share a common origin and are gravitationally bound for some length of time. The two basic categories of star clusters are open clusters and globular clusters. An open cluster is a group of up to a few thousand stars that were formed from the same giant molecular cloud and are still loosely gravitationally bound to each other. Open clusters are found only in spiral and irregular galaxies, in which active star formation is occurring, and their stars are usually young. In spiral galaxies, open clusters are found in the spiral arms and are concentrated close to the galactic plane. In irregular galaxies, open clusters may be found throughout the galaxy, although their concentration is highest where the gas density is highest. Over time, as these clusters rotate around a galaxy, gravitational disruptions from passing cosmic objects can cause the stars to disperse, but clusters members will continue to move in broadly the same direction through space even though they are no longer gravitationally bound. They are then known as a stellar association. Open clusters are not seen in elliptical galaxies because in these galaxies star formation ceased many millions of years ago, and therefore the open clusters that were originally present have long since dispersed. Globular clusters are much larger and denser than open clusters, containing thousands to millions of stars, all formed from a shared nebula. Unlike open clusters, the density of stars at their centers is so high that it is difficult to discern individual stars. There is no gas or dust in a globular cluster, and the stars are old. Globular star clusters are associated with all types of galaxies and can be found throughout the halo or other regions of galaxies. The third astronomical object you should know about is called nebula. The word nebula comes from the Greek word for cloud. A nebula, the plural of which is nebulae, is an enormous diffuse cloud of interstellar matter. Interstellar means between the stars, mainly gases, hydrogen, helium, and other ionized gases, and dust. A nebula forms over a very long time because of the gravitational attraction between the masses involved. How stars are born in clouds of gas and dust, nebulae are known as stellar nurseries. There are several kinds of nebulae, with different origins and different sizes. We will see five main types of nebulae in the universe: emission nebulae, reflection nebulae, dark nebulae, planetary nebulae, and supernova remnant. Emission nebulae are clouds of high temperature gas. The atoms in the cloud are ionized by high energy ultraviolet photons emitted from a nearby hot star and emit radiation as they fall back into lower energy states. Emission nebulae are usually red because hydrogen most commonly emits red light. It is usual for a young star to ionize part of the same cloud from which it was born, and in many emission nebulae, an entire cluster of young stars is doing the work. In some nebulae, the star formation regions are so dense and thick that light cannot get through. Not surprisingly, these are called dark nebulae. A dark nebula is an interstellar cloud of cosmic dust that is so dense it absorbs, scatters, and blocks visible light. Although dark nebulae may seem like lifeless cosmic objects, important events actually occur in the inner regions of dark nebulae. Hydrogen molecules form and stars are born. These stars are often hidden from optical light due to the density of the dark nebulae in which they are born, but radio and infrared telescopes allow astronomers to peer through the cosmic dust and get a closer look at the star formation occurring within. Another type of nebula, called a planetary nebula, results from the death of a star. When a star, like our Sun, has burned through so much material, nuclear fuel, that it can no longer sustain its own fusion reactions, the star's gravity causes it to collapse and dies. The star expands to form red giants. The dying star will continue to expel gas, whilst simultaneously the remaining core of the star contracts, its interior heats up, and temporarily begins to radiate energy again. This energy causes the expelled gas to ionize, meaning that the atoms and molecules in the gas became charged and began to emit light. The cast-off glowing gas is known as a planetary nebula. Therefore, planetary nebulae are classified as emission nebulae. The dying star's core becomes a white dwarf. The life of a star whose mass is greater than 1.4 times the mass of the Sun ends more violently and leaves behind a different type of nebula called a supernova remnant. When a massive star runs out of nuclear fuel and collapses, an enormous shock wave sweeps through the star at high speed, blasting away various layers and leaving behind a core called a neutron star and an expanding shell of matter known as a supernova remnant. Near the core of the remnant, electrons emit radiation called synchrotron radiation as they spiral toward the neutron star at speeds close to the speed of light. The ultraviolet portion of this radiation can strip electrons off or ionize the outer filaments of the nebula, causing them to glow. Reflection nebulae are clouds of dust and gas that are near enough to a light source as to reflect the light, but not near enough to be ionized. Energy from nearby stars is insufficient to ionize the nebula's gas to form an emission nebula, but sufficient to provide enough scattering to make the dust visible. Many small carbon grains in the nebula reflect the light. The blue color typical of a reflection nebula is caused by blue light being more efficiently scattered by the carbon dust than red light. The fourth astronomical object you should know about is quasar, quasi-star object, abbreviated QSO. Quasars are intensely bright, powerful cores of distant galaxies, powered by a huge disk of particles surrounding and falling into a supermassive black hole. The gas and dust in orbit swirl around the black hole with such ferocity that as they circle and fall toward the black hole, the gas reaches temperatures exceeding a billion degrees. At these extreme temperatures, the gas creates enormous electric and magnetic fields. These electric and magnetic fields, in turn, shape the gas and shoot it out in the form of long, thin jets of relativistic plasma. These jets emit large amounts of radio emissions, the signature of a quasar. The fifth astronomical object you should know about is the dark matter. Dark matter is the name given to the proposed matter that must be present in the universe, but which has never been detected directly because it neither emits nor absorbs radiation. Although dark matter is not detectable with current instruments, scientists are confident that it exists due to the gravitational effects it seems to have on visible matter. For example, one of the strongest evidence for the existence of dark matter is that stars at the edges of rotating spiral galaxies should travel much more slowly than those near the galactic center, where a galaxy's visible matter is concentrated. But observations show that stars orbit at more or less the same speed regardless of where they are in the galactic disk, which leads scientists to believe that something we cannot see is at work. This intriguing result makes sense if we assume that neighboring stars are feeling the gravitational effects of an invisible mass, dark matter, in a halo around the galaxy. Many theories have been proposed about the nature of dark matter. WAMP, neutrino, and Mitchell are three of the most popular dark matter candidates. MACHOS is an acronym for Massive Astronomical Compact Halo Objects. These could be old stars or small failed stars, very large planets, or even black holes. any or all of which simply do not emit enough radiation for us to detect them. It is considered unlikely that there could be a sufficient number of such objects to explain dark matter fully. WIMPs is an acronym for Weakly Interacting Massive Particles. Note that here massive simply means with mass. It does not imply large individual masses. There could be very large numbers of particles that we do not know about yet simply because they are very difficult to detect. Neutrinos. The masses of neutrinos are presumed to be very small, but they are still not known with any certainty. Neutrinos are present in the universe in vast numbers, so they could contribute significant mass. There are many other astronomical objects, but in this video I tried to give an overview of the largest structures of which the universe is made. Stars, pulsars, black holes, comets, asteroids, and stellar evolution will be studied in detail in the next videos. For those who want a good introduction to astrophysics, do not miss the next videos.